Hello, everyone. My name is Oscar Alvarez. I'm from the Department of Mathematics at the University of Texas at Arlington. I'm here to show you how to calculate Liutex using MATLAB. Now, this isn't going to be an in-depth coding tutorial, or it's not going to be a in-depth explanation about Liutex. It's just going to show you how to program it in MATLAB so you can use it for your own software. So I'm going to start a new file, and I'm just going to call it liutex.m because our function name has to be the same as the file name. And I'm going to open it up. Now on the right, these are the instructions on how to calculate Liutex. So we're going to follow these instructions and see if we can calculate Liutex. I have my notes over here on the right. So we're going to calculate, so we need to create a function. It's going to return big R and little r. And those are Liutex. And it's going to take in the velocity gradient tensor. Now, this is assuming you've already calculated the velocity gradient tensor. So, and big R is the Liutex magnitude, and little r is the Liutex vector. So let me just go ahead and explain what this function does. This function returns the Liutex magnitude, big R, and the Liutex vector. Oh my goodness. R when given the velocity gradient tensor, which is a 3x3 matrix for a 3-dimensional flow field. So this is assuming your data is in 3 dimensions, and the little r is the Liutex vector itself, and then the big R is the Liutex magnitude. So let's go ahead and start coding. I'm going to save the velocity gradient tensor as variable A because I do not want to type velocity gradient tensor a lot, so I'm just going to name it A. And the first thing that we have to do is extract the eigenvalues from the gradient tensor. So that's what we're going to do. Now MATLAB has a fancy way of doing this, very simple. It returns the eigenvectors and the eigenvalues in an array. And these are two matrices. So the velocity gradient tensor is always going to be a 3x3 matrix. So we should get 3 eigenvalues, and these are their corresponding eigenvectors. And they're returned in a 3x3 matrix, where the columns are the eigenvectors and the diagonal are the eigenvalues. And we're going to take the eigenvalues and eigenvectors of our velocity gradient tensor. Now, we need to check oh my goodness. Check if the eigenvalues of the velocity gradient tensor are all real. If they are all real, then Liutex is equal to 0. So this is the big idea behind Liutex. The big idea behind Liutex is that using the velocity gradient tensor and whether its eigenvalues are complex or real, we can determine the rigid rotation of the fluid. So if all of the eigenvalues of the velocity gradient tensor are real, then there is no rotation. If there is no rotation, then Liutex is 0. So we're just going to go ahead and do that first. So so if there's a cool function that determines if an object is real. So when I calculate these eigenvalues, it's going to return two objects, two matrices. They're objects and matrices. If there's complex eigenvalues in the velocity gradient tensor, then this object will be a complex object. This will have complex values. So these will be complex objects. If the eigenvalues are all real, then there won't be any imaginary parts to these. They'll just all be real. So if they're real, then we have all real eigenvalues. So I can check if the eigenvalues are all real by using this function. And if they are all real, then the Liutex magnitude is equal to 0. And the Liutex vector is equal to 0. And there are three components to the Liutex vector, the x, y, and z direction coordinates. And then I'm just going to return because I'm done. I'm finished calculating Liutex because my velocity gradient tensor gave me all real values, so there's no rotation for the eigenvalues. But what if there is no, what if we do have complex eigenvalues? Well, if there exist complex eigenvalues, then we'll continue to calculate Liutex. So there exist complex eigenvalues, let's say, and we need to calculate Liutex. So to do that, we need to determine which eigenvalues and eigenvectors are real and which are complex. So using this function, it's not guaranteed the order of these eigenvalues and eigenvectors. That means that we don't know if the first eigenvalue is real or the first eigenvalue is complex. So we need to know which one's which in order to extract the information that we need from them. So, so I'm going to loop through each of the eigenvalues and see if which one's real. So for I 1 through 3, since I know it's going to be a 3 by 3, if the imaginary part of the eigenvalue that I'm looking at, remember this is the eigenvalue is a diagonal matrix. The eigenvalue matrix is diagonal matrix where the diagonals are the eigenvalues. So I'm going through each of the eigenvalues of this that I'm given. And if the imaginary part of the eigenvalue is equal to 0, then I know that eigenvalue is real. And now that I know that this eigenvalue that I'm looking at I, well, that's real, so I want to save that index. So I know that the real index is equal to I. So I found the real eigenvalue. Now, because this is a 3 by 3 matrix, the matrix can only return 3 real values or 1 real eigenvalue and 2 complex conjugate eigenvalues. So if there's 1 real value, there's going to be 2 complex conjugate eigenvalues. So I found the real one. So any other index is going to be imaginary. So what I'm going to do is I want to find the imaginary index, or an imaginary index. And I'm going to do this using modulo, or mod, because the dimension of the matrix is only 3. It only has 3 columns. So if I increment my index, right, take this one and go over 1, I could overflow and go to 4, and then it would not like that. So I'm going to mod I by 3, And then because this number produces a value from 0 to 2, right? Because if I equals 3, then it becomes 0. In MATLAB, all indices for the objects start at 1, so I'm just going to increase it by 1. So if I'm at the last column, then this will be 0, and I add 1, and then I will be at the first column. So basically, I'm moving over 1, and if I reach the end, then I will loop back at the beginning. So that's an imaginary index. So now I've figured out which eigenvalue and which eigenvalues are real and which value is complex. Now these are corresponding. So if the first eigenvalue is corresponding to the first eigenvector in this eigenvector list. So what do we need to do first? Well, I need to save the real eigenvector of the velocity gradient tensor. So I know which one is the real eigenvector because I have the real index. So I'm going to save the real eigenvector as the eigenvector, and it's the whole column, and it's of the real index. Now, because we've already determined, if we're already down here, we know they're complex eigenvalues. What's going to happen is this is going to return an entire complex object, here. So even though there's no imaginary part, as in the imaginary part is equal to 0, I just want the real values. So I'm just going to get the real values of the eigenvector. And that's going to be my real eigenvector. Now, the next part I need is I need to save the imaginary part of the complex eigenvalues of the velocity gradient tensor. So for the eigenvalues, like I said, if they're complex eigenvalues, they'll be complex conjugate eigenvalues. That means that the imaginary part is going to be positive, that they're going to both have the same imaginary part. They're just going to vary by sign. So I just want the imaginary part of the complex eigenvalue, any one of them, and I have the imaginary index, so I know which one's imaginary. So I'm going to call this, and this is called lambda ci in the papers, and it's known as lambda ci. I just want the imaginary part of the eigenvalue. And because the eigenvalue matrix is a diagonal, I need to get the imaginary index, So this is the, whatever I this is going to give me the eigenvalue for the imaginary part. The imaginary part of an imaginary eigenvalue, which is what I need. Okay, cool. So now I have the real eigenvector of the velocity gradient tensor, and I have the imaginary part of the imaginary eigenvalues of the velocity gradient tensor. Now I need to calculate vorticity. Now I need vorticity using the velocity gradient tensor. Vorticity can be found different ways, but since we have the velocity gradient tensor, we can just use it to calculate vorticity. So it's a pretty simple formula, and I'm going to spare you me typing it. I'm going to just copy from my notes. And we basically have, it's a vector, and the first component is the third row, second column of the velocity gradient tensor minus the flipped part of these. And that's just how it is for using the velocity gradient tensor. So that's how we calculate vorticity here. And after we calculate vorticity, I need to check the first condition. So what is the first condition? The first condition is if vorticity dot product, the real eigenvector, is less than 0. So here's the first condition. It's pretty self-explanatory if you read the if statement. So I'm going to take the dot product of vorticity and the real eigenvector that I got. And if that dot product is less than 0, that means that it's negative, then I'm going to flip the direction of Liutex vector. So real eigenvector. And if it is not, then Liutex is going to be just the real eigenvector. Okay, so this checks the first condition of Liutex and sets our first instance of the Liutex vector, which is lowercase r, little r. Now that we did the first condition, we need to find big R, which is the magnitude. So now we need to find the Liutex magnitude. And there's an explicit formula, which you can just look at my formula that I'm about to type on screen. And we use omega to represent vorticity. So I don't have omega here. I'm just going to use a W. And the first thing that we're going to need is the dot product. So omega dot R, which is vorticity dot R that we just calculated. And it's just the dot product of vorticity and R, lowercase r, that we just found. And here's the explicit formula. So the Liutex magnitude, big R, is equal to W dot R minus the square root of W dot R squared minus 4 times lambda CI squared. So that is the explicit formula for Liutex magnitude. Excuse me. Now that we have the Liutex magnitude, we need to apply the Liutex magnitude to our Liutex vector. So the Liutex vector is equal to the Liutex magnitude times R. Oh, little r. And we're done. We just return. We return, and that's the end of our function. So that's how we calculate Liutex. This is the code for Liutex. That's how we calculate it and using MATLAB. So let's test to see if this function works. So I just saved it, and I'm going to create a new file, and I'm gonna call this testing Liutex function. Okay, and I'm going to save that. I'm going to say test Liutex.m. Okay, so I already kind of wrote a script. So what I'm going to do is let me just exit out of here. I'll just write it, and we'll go along with it. So I want to clear all variables, and I want to CLC. That's just something you want to do in MATLAB. So I'm going to test the Liutex function, and what I'm going to do is I'm going to try testing the Liutex function with a velocity gradient tensor. So this is just pretend, right, that we got this 3x3 matrix that has all real eigenvalues. So if you have 3D velocity field, and let's say that this is the velocity gradient tensor that you've calculated at that point. I know that this matrix has real eigenvalues, so let's test Liutex to see what comes up. So I'm going to use my function. It's going to return the Liutex magnitude and the Liutex vector, and I'm going to test Liutex, and I'm going to input it this real velocity gradient tensor. Now I need to see what happens. So fprintf real eigenvalue results and dash end, and then fprintf big R, that's what we got first, and then this G, just a general object, so it knows what to print, and that's going to be our R that we got, and copy paste, and this is going to be our Liutex vector R. fprintf space. Okay, so we have a velocity gradient tensor with all real eigenvalues. I know for a fact that if the velocity gradient tensor only has real eigenvalues, then there's no rotation and Liutex should be 0. So if I run this function, I should get these equal to 0. So I'm going to go ahead and run. And here's my command window. It's very small. I don't know if you can see that, but let me copy paste that up here. And you can see that we got 0 for the Liutex magnitude and 0 for all the Liutex vector, every component. So that works. So we got a working. If it has real, then it just stops and it's all 0. But what if there's a complex velocity gradient tensor? Well, I have an example for that too. So here's a velocity gradient tensor that has complex eigenvalues. So again, I'm going to produce my Liutex magnitude and Liutex vector. I'm going to call Liutex, and I'm going to use my imaginary velocity gradient tensor. I've already did the results here, and this is going to be complex eigenvalue results. So this 3x3 matrix represents a velocity gradient tensor, and this velocity gradient tensor has complex eigenvalues. So this will produce this has complex eigenvalues, so in theory we should get Liutex to be a positive value or a value that's not 0. So let's see what happens here as I run this. So it's going to print the real one first, and it's going to print the imaginary one second. So I'm going to run, and look at that. The real values are all 0, and the complex eigenvalue results, we get a non-negative result. So if I separate these, we have the Liutex magnitude is a real value. It's a positive value, so we have rotation. And we have the Liutex vector here, also non-zero. So we can see that our function is working just fine. And now hopefully you can implement this in your software so you can use Liutex for a more accurate representation of a vortex. So thank you very much. That's it.